Welcome to Modern Atomic Theory again. This is the very last video, so that should be wonderful for everyone to know. And now that you are aware of how electrons fill up apartment buildings, let's go ahead and learn how they fill up real orbitals and how we can write that. So instead of stinky roommates, we're going to really talk about electrons today. And we're going to start with the most simple atom of all, and that is hydrogen. And hydrogen has one electron. It has one proton, and therefore it has one electron. So for a neutral atom. Here I have written out orbital diagrams. And orbital diagrams look surprisingly similar to apartment buildings. And instead of representing each electron as a bean in a little circle, we're going to represent each electron as an arrow, either spin up, as in the hydrogen atom, or here there's one that's spin down. So if you'll remember, you can only put two of them in an orbital, and they both have to spin different directions. That was the Pauli exclusion principle that you learned about earlier, and it's important because the electrons cannot occupy the same space. They cannot have all four of the same quantum numbers. So here we have a 1s orbital diagram with the electron spinning really however it wants to spin, because there's only one of it. When we write the electron configuration, we simply say that that electron here is in the 1s orbital, and there's just one of it, one electron, and there it is. So 1s orbital with one electron in it. When we add one more electron, we come up with helium. Helium has two electrons. Here I've represented both of those in the 1s orbital. So the electron configuration for helium would be written 1s, because it's in the principal energy level 1, the s orbital, and there are two electrons. So 1s with two electrons in it. Lithium, we're going to add one more electron, and the orbital diagram looks like this. We still have two electrons in the 1s orbital, and the 2s orbital has one electron. It's written 1s2 and then 2s1. The 2 is for two electrons in the 1s orbital, and the little tiny 1 is for one electron in the 2s orbital. Here is beryllium. We write that 1s2, 2s2. So there would be two electrons in the 1s orbital and two in the 2s orbital. So if we were to write that in over here, we would have, get color on here, we would have one electron pointing up and one pointing down. And then we go to the 2s orbital, one pointing up and one pointing down. So let's see if you want to pause for just a minute and see if you can write the orbital diagram for boron. Okay, for boron, we have 1s2, there's two electrons there. We have two electrons in the 2s orbital, and we have only one electron in the 2p orbital. Boron has a total of 5 electrons, so that's where those all sit. So let's look at the next slide. Okay, here, it just continued with carbon. We added one more electron, and it's important to note that electron does not reside in the first sublevel of the 2p subshell. So P has 3 orbitals in it, and each of those electrons, just like in this stinky roommate analogy, each of those electrons wants to be far away from each other, so they will fill up this orbital, then this orbital, and then this orbital before they come back and start filling. You can see that here. We fill up this orbital, and this orbital. Sometimes it's designated 2px, 2py, 2pz. And here we finally come back and fill up next to the first one. Here we're going to fill up next to the second one, and here is our neon, which is our noble gas. It has a full octet in the principal quantum number 2, the principal orbital 2 energy shell. Right here, there's, you'll count them, 2, 4, 6, 8 for its valence electrons. And there's something else that's interesting to note, and that is that the valence electrons are often used in a special shorthand notation. Neon would be an example of that. If you have an element that comes close after neon, here's neon on the periodic table, such as sodium or magnesium or really any of these prior to getting to argon, you can use a noble gas shorthand. And let's take sodium, for example. If we want to represent sodium, we can represent that by simply saying neon, and then we see that sodium has a 3s1, and that's just a simple notation sometimes that's used. So here, write the electron configuration for magnesium. If you'll pause, you can do that, and then you could also write this configuration using the noble gas shorthand just below it, and then come back on and we'll do the problem together. Okay, electron configuration for magnesium. Magnesium has 12 electrons, so we're going to start writing those down. 1s2, 2s2, 2p6, it's going to be full, and then we have 3s2. And if we want to write that in shorthand using the noble gas configuration, we use neon, and then here you can see magnesium is going to have 2 more in the third energy level, so it has 2 more electrons, so 2s2. Now it's important to remember, and you know that from your quantum apartment building game or activity, that orbitals fill up lowest energy first. So let's take a look. You kind of are familiar with this. I think you've already seen this chart, but when we have, let's say, nickel, for example, nickel has 20 electrons, and it's going to, since it has so many electrons, it's going to do some different things here. We're going to look at fill up 1s orbital first, then the 2s, then the 2p and 3s, then come back up, the 3p, then the 4s, and come back up, then the 3d orbital, and that is where our 20 electrons will reside, and you can see I wrote that configuration out right there. But we don't go directly from 3p to 3d because 3d is actually higher energy than the 4s. So here's your little illustration, and you can use that to help you remember the energy levels and how they increase in order. Another way to remember energy levels that's really a neat way on the periodic table is in blocks. We have our S block right here, and you already probably have realized this, but I'll just point it out. All of these elements have their valence electrons in an s orbital. So helium is also included in that. It's part of the s block. So hydrogen is in the 1s orbital. Lithium and beryllium, they have their valence electrons in the 2s orbital. And sodium and magnesium as well. All of these have their valence electrons in the s orbital. They're just in different energy shells. The p block over here is just the same, only these elements have their valence electrons in a p orbital. And the only difference, again, is the energy level. These atoms here are all in the 2p orbital, and these are in the 3p and 4p, and so on. This is the d block. And once again, the atoms here have their valence electrons in the d orbital, and this is the f block. and as they follow the same pattern. So it's interesting to note this because the groups of atoms behave very similarly when they bond and when they combine with other atoms. The noble gases obviously are very inert. They all have a full octet. The halogens behave in very similar ways. Each of these groups behave in very similar ways, and it's largely due to the fact that their electron configurations are the same, other than that they are in different energy levels. And I've been using this word, but just to define it, valence electrons are, if you didn't already know, they are electrons in the highest principal energy level of the atom. So the valence electrons for, say, beryllium, 2s2. Those are its 2 valence electrons. And fluorine has 7 valence electrons. They happen to be in the 2 of them in the 2s orbital, and the other 5 of them are in the 2p orbital. So the core electrons are the ones that are not the valence electrons, obviously. Sometimes they're called inner electrons. They're not involved in bonding. Just the valence electrons are involved in the bonding. So now you get to try. So you can go ahead and pause the screen and write the electron configuration for strontium. Try that one. Write an orbital diagram for silicon, and write the electron configuration using noble gas shorthand for potassium, and see how you do. Here are the answers. We have strontium with this electron configuration. We have silicon with this orbital diagram. Now here I drew the orbital diagram with circles rather than little squares. Either one is fine. You might see them more often with circles rather than squares, but either one is okay. Potassium, here is the noble gas shorthand for potassium.